Everyone, it's September 11th. Alright, let's... Oh, shoot. What did I do? Okay, let's get to it. What we have now is bag of tokens. We have initial power, initial score of 0, and a bag of tokens, where tokens I is the value of the ith token. The goal is to maximize your total score by potentially playing each token in one of two ways. If your current power is at least token I, you may play the ith token face up, losing token I power and gain 1 point. If your score is at least 1, you may play the ith token face down, gaining token I power and losing 1 score. Each token may be played at most once and in any order. You do not have to play all the tokens. Earn the largest possible score. So, if I have power, that's the current power, and I can play any token I want. If your current power is at least so larger than equal to this, I can play the ith token face up. I can play it face up. I'll lose token I could be 0, and I gain 1 score. If the current score is at least 1, and I can play any ith token, I can play it face down to gain. So I can either, so if it's 0, then I cannot lose score, so I cannot do this. But if I am at least 1, I can pick any token, and I will gain the power, but lose a score. Or I can take any token that's larger or equal to this. I will lose the amount of power and gain a score. So now we want to see the largest possible. So we have 100. Oh, that's only 1, so it's not possible. Here I can play 100 to gain 1 point by losing 1, so I have 50. So if I have 50, I can play this token, which will get 200, become 250, but I'll lose a score. But why would I lose a score, right? Okay. What does this remind you of? It seems DP to me. Because if you think about it, each token, well, we have 3 situations for each token. It's either played or face up. Ooh, actually, we can always play something face up. The face down is dependent. Let me think. So each token can only be played once, at most once. So let's say we have a starting power, alright? So if we have any token that is smaller than that value, so those tokens can only be placed face up, which will minus and we can gain power. So if I can get the power as high as possible, okay, so if I sort the tokens from small to large, right? Okay. To gain more power, we will lose score. Right? So the first step is always to lose some to get at least 1 point. If we can get, because if not, there's no other move. It's always stay 0. So our first step definitely is to play the smallest token. If we play the smallest token, we gain 1 point, right? And then the idea should be to play the largest token face down, because we have at least 1 score. And if I play the largest token, I will gain the most power. So potentially, I can take the next smallest, right? So are we talking about a scheme of always face up, go with the smallest, then face down, go with the largest, and then smallest, go face up with the smallest, face down with the largest, front and back, front and back, front and back. So this kind of scheme will guarantee every time when we regain the power, we'll regain the maximum power possible, right? Maximum power possible. So now the question now is, once we get that, we should actually keep popping as much small as possible under the current, right? Because it might be possible that the current highest power can satisfy the entirety of the rest. So I have to play the first token face up. No, face down. I have to play that one. No, I have to play the first one face up. We have to give up that power for sure to gain a point. And after that, I'll take the last one, become 0, and then we record the score along the way. And then we will pop the front. We just go. If we have more, we just keep going until we cannot go anymore. Then we add more. It's kind of greedy. I'm gonna try it. Can you prove this is the best? I mean, the proof can just be that we know, right? To get the maximum power, we need to remove the power. We need as many tokens as possible. We need to deduct the power as many as possible. So we should deduct always the smallest. So that allows us the maximum amount of deduction. And then, if we cannot have any more to deduct, we need to bump up power. Then we should bump up the maximum power currently available. So let's try this. But before we do that, alright, so what we have is this, and we need to go tokens.sort. Right, let me sort this. And then rest equals 0, right? That's the score. And ij equals 0 and length tokens minus 1. Then we say while while true. Wait, no. While I is smaller than j. I is smaller than j. Maybe it should be smaller or equal to j. Because if they meet in the same value, j is the largest one. When we use it, we'll go here, right? But I is the smallest one. When we use it, we'll go here. So if they meet each other, that means this one has not been used. Oh, I is smaller or equal to j. Okay. Then we say while power is larger or equal to, because we can, is at least, right? So if larger or equal to tokens I, score, and the score, res score. Score is constant changing, right? So that's the case, then score plus equal 1 and power minus equal to tokens I, and I plus equal 1. Then we try the next one, then we try the next one, and then we try the next one, and it doesn't work. Okay, so we break out. Now whenever we break out, we say res equals maximum res and score. Right? After that, the power is smaller, so we need to add one more. Otherwise, we have nowhere to go. And we say power plus equal to score, no, tokens j minus equal 1, and score minus equal 1. Right? Then we go back. If they're equal, we always try. And then when we jump out, we're going to return the rest. Okay. Let's try this. Row. One. Two. Power bag of tokens. Seem to be right. Could be 0 in length. Okay. It's alright. Oh, the hell. I bet it's the same mistake. Index out of range. Oh, yeah. Well, I smaller equal to j, and yeah. Now we have a wrong time, wrong answer. Man, lately the streak is not very nice. What are we supposed to have? Oh, I need to record this one as well. So it should be 1. Or index out of range, sure. While I smaller equal to j, and alright, so for this one, power is 54, right? So the first step must be add a score. So we will do oh. How did that happen? This has to larger equal to, well, it's not. Oh wait, it is. Oh wait, it's not. It's 55. So the rest is 0. Then power will add to this. Oh, we cannot add power. Oh my god. If score. Then we do this. Oh, that's if score. So the score is not. Nobody's making changes. Nobody's making changes. That's interesting. So I shall say, if after this the score is 0, which means we just cannot make any move, right? So yeah, I can still do this way. What we say is after this, if not score, right? Which means it's impossible to even get a single score, then we shall just break, right? We should just break. We cannot play any token, right? To get at least one score. If that's the case, then, because if you don't have any point, you can't do this. Then we just break. I could have just put this one up, right? Say score larger equal to 0. Well, I can avoid doing this computation. Some caveats. $801 days. Alright, so oh wow, last time 2 years ago. $9.48. So greedy. Always deduct power from the smallest token. If that is not possible, and there is a score left at the largest token to have the best chance of further acquiring points. One caveat is that, not caveat, one thing to note is that whenever there is no way to earn any point, and whenever there's no way to earn any points and the current score remains 0, we cannot progress, because with 0 score, we cannot add more power to the. We cannot add more power. So, Owen, that was a pretty smooth ride for this one. This is exactly what I had now. What was the initial solution? A little bit confused. Yeah, I think it's the same idea. Anyway, that's that. So let's go back to this thing. I checked the. It's not this problem. It's this one. Right? I checked that solution. Now I kind of have a better understanding of this problem. Yeah, because this one's still not working, right? This one's still not working. So solution number 5. Lordy. We have solution number 5. This is the solution from a sample. This is from a sample solution. From a sample solution that scores that runs very fast. It has the same idea as solution 4, where we pick but with a few important changes. First, we go row-wise, right? Because the max value can be computed simply by max row. 2, we compare the mid row to the bottom row. If max of mid row is larger than that of the bottom row, if it's larger than the bottom row, and we shrink, we discard the bottom half, not including the middle row. Right. This makes sense, right? It makes sense because we preserve the apparent larger option. Yeah, that is, and then we put that into the last row. And then we try it again. Eventually we'll come down to 2 rows. Then just every time we shed, right? We know this is larger than this, and this is larger than the bottom, right? So we shed the bottom, and then we try it again. So this is smaller than we shed the top half. Eventually we have this. If this is larger, then wait, how does this work? Wow, I don't think it'll work. How do you only compare 2 rows? And you can't guarantee. I don't think it's right. I don't think it's right. What is I? I equals mid. High is mid minus 1. High is mid. I don't understand. What about everything in between? I feel like I can counter this very easily. If this is larger than high, and high equals mid minus 1. Yeah, how is this one correct? Yeah, this one's not correct. You can't always rely on these things. Not correct, but it does give me an idea to go row-wise, right? Maybe go row-wise is faster. Okay, I'm gonna go row-wise. So this is going to be n minus 1. Mid. Then we have let's say max mid, right? Max mid, mid up, max mid minus 1. If mid is larger than 0 or minus 1. Down, and then plus 1 if mid is smaller than minus 1 or minus 1. So we have up and down. Say if max mid larger than max mid up and max mid larger than max mid down, then you return mid and max mid dot index max mid. Okay. Else if only 3 situations, right? Mid up larger than max mid and max mid up is larger than max mid down. If mid up is the largest, then we simply say mid minus aleph max mid down O equals mid plus 1. Like this. Okay, solution 5. So what's the else? Oh, n minus 1. My bad. What the hell? What's the difference? You take the max value, 4, 3, and fail the second one. Oh, rest is 2, 2. 2, 2 is good. So the other one is good. And let's put 2, 2 in. Anyway, let's just swap into oh, we don't need this. Okay, the rows are, yeah, maybe I just cut very close. Oh no, this is basic, this is not working. This is not working. Why? It's 0 and 4, we're not changing. There's a situation we don't consider. I think we're having the issue of repetition. 18 and 18. 49 and 49. I can just say larger equal to. Yeah, I just go larger equal to because adjacent won't be the same, so it should be safe. This. Once it is correct. But this is the same. Oh, slightly faster. Now we'll go back to slightly faster. Why would this work? Apparently it works, right? Oh, we have more. Yeah. If max mid is larger than max high, mid is larger than high, then high equals mid minus 1. I'm going to record this. And we say we don't care. We'll try it again. So every time I keeps track with the one that's larger. If it's smaller. This is smaller than this. We don't move I. So I will always be the larger middle, right? But I always stay with the larger middle. I stay at the bottom. Then I pick the larger of the two. The question put it here. What is the larger of the two? So what's the justification of throwing the second half? I don't have insight into this. What's the insight of throwing the half? Insight of throwing away the half. If the middle row is larger than the bottom row, so we can make an argument, because we only need to find one peak, right? So if the middle row is larger than the bottom row, if the row underneath it is smaller, then it's legit, right? It's legit. If the row under it has bigger value, and the exact place we have a bigger value, how do we handle that? Right? So what I'm saying is, if a row has a big value, and a row beneath it has an even bigger value, like I said, this is, let's say 5, this is, say 6, okay? I don't know. Let's say in this one I have a 5, and this one has a 6. This one has a 1. Right? Then we take this, then we go up. Let's say we try to find maximum. If this one's larger, I'll put it in here. Okay, it works. If this one's larger, we'll put it in here. the I keeps track with a larger one. If if it's larger, keep track on the top half. And if this one is larger, or for the bottom row, then it works. Wait, hold on, how does it work? We're just comparing the two. Say if this one larger, so let's say 4. And this one also 1. Like that. Under my scheme, I go here, 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 largest one here. So we check this one, and this one we check in here. Then we get it. But in their scheme, we'll compare the middle, the bottom, middle is larger, so we go check these two. And this is larger. 0, 1, 0, not this. Larger than no. Ooh! If mat mid is not larger than, then we don't change the I. The I still stays here. Alright, let me think again. So we do a middle versus the bottom. If the middle, right? If the middle is larger than the bottom, the middle, I put the I into the middle, okay? Then we compare the others. And if middle is larger than this, then we go up. So every time middle is larger, we move the battle up. Move the battle up. Alright, so the middle is bigger. We'll move the battle up and make that as the bottom row. I don't care anything that's down. Alright? So middle is bigger. I'll move the battle up. And then I'll move the battle up. If the bottom is bigger, then we move everything down, but we don't change it. If sine so if it's a 6, so 5. Now mat mid is 1, larger than this. No, low equals mid plus 1. So low and high is equal, common high. I don't know. So 1, 6, 5, 6, 1. Yep. It's not right. The solution is not right. So let's check the discussion. And this is m log n already. Yeah, I already know the binary search is correct. I was just not sure the top answer is correct. So this is actually a good lesson. The top answer, the sampled answer, is not always correct. Exactly, finding p element. Oh, it's the same thing. They pick the middle, pick left and right. Right? If the middle is the biggest, we're done. If right is the biggest, then we go to the right. This one can be the biggest. Right? We go to the right half and pick again. So if this is bigger, we just keep going right until like if it's reached the right boundary, so which that is good. If it's smaller, if at a certain point the right is not, something, say the left is the bigger one, right? So we're encoding this is the left. Oh, wait, hold on. Then so this is bigger. So we go to this one, right? This is bigger. Eventually, so it'll be bigger. So the bigger ones just converge until we have, say, 2 or we have 1, and that's the biggest one locally. Yeah, it's bigger than everything to this side. This one's bigger than everything to this side, and then whichever is bigger. Yeah, it makes sense. Yeah, so this is actually good. We solved this. There's no solution 6. This solution is wrong. But this solution is nice. Alright, that will be it. I will see you guys tomorrow. Adios.